Good morning, students. This is the first class that I am taking in the online media, online platform, that is the Google Classroom. This video has been made for your better understanding of the study material that I have given you. Now, yes, the previous class we have discussed and we have designed the beam, how to design a beam, how to design a purlin we have discussed, and up to that was in your slot syllabus. Now from today on we will discuss about design of compression member, that is the column. What is a compression member? The member which is subjected to compressive load at its both ends. If this is a column, if P load is acting here at the bottom, a reaction similar to P load will be acting. So that's why it's a compressive force. Now, in a RCC building, the compressive members are called, in general called columns, and in steel building, they are generally called stanchion. So there are two terms, columns and stanchion, in the RCC building and steel building. And for roof truss members, the compressive member are called truss. You know what is a strut. When you are using a compressive member in the roof truss, this is called strut. Now, when we have to design a compressive member, some basic features of the compressive member as per the IS code we need to be clear about. We need to be clear about what are the basic features of the column, what are the basic criteria, basic parameters that we need to consider first for the design of column. First is the effective length of the column. When we are doing the effective length, first we know what is the effective length. Consider this picture. In this picture, the column is fixed at the both ends. If the loads are there at the two ends, the loads is applied, the beam, the column will buckle like that. Now, buckle at these 2 points. The column will buckle at this point and this point. This point at which the column buckles is called the point of counterflexure. Okay, now the distance between this point is called the effective length, that is the LE is called the effective length. The effective length for a column is generally determined by this formula. For normal column, that is the LE into K into L. For the normal columns, normal steel columns, this is the formula of LE into K is the effective length factor. Now the effective length factor is determined for table 11 of IS 800. Now if we go into the table 11 of IS 800, we can see that if it is a table 11 of IS 800, now if in the IS 800, in the table 11, we can see the column conditions are given, the effective length based on the end condition. Number one, end condition at one end and other end, rotation and translation, that means horizontal movement and vertical movement. Depending on the fixity of the boundary condition, we determine the effective length factor K value from here. Okay, so this is the effective length K factor, and the L is the center to center distance of the intersections with supporting members. So center to center distance is the intersection. So this is L and this is LE. Clear? Now this is for the normal column. Now sometimes the column may be from a frame section. When the column is of a frame section, in the frame section the number of columns and beams are joined at the point. Now when we are discussing the column section in a frame, then the effective length factor for column is differentiates by these two formulas. Number one, for the non-sway frames and sway frames. What is the non-sway frames? The frame which will be not braced, that means there will be horizontal movement in the frame. Okay, there will be horizontal. If this is a frame, if this is a non-sway frame, the frame will move like this. Okay, I think you know from the structural analysis. Okay, it is called the sway frame. and if the frame is braced, again its movement, it is called non-sway frames. So depending on the sway and non-sway frames, there are the two effective length factor. It is based on the clause D1 and D2 of IS 800 of page 123. This is page 123. This is for the non-sway frames and this is for the sway frames. This is the formula, this is the formula. What is the B1, beta 1 and beta 2? Beta 1 and beta 2 are given by this formula. Summation of K by summation of Kc by Kb. Now, summation of K, summation of Kc by Kb. Now, what is Kc1, what is Kb? Effective flexural stiffness of column and beam meeting at the joint. Consider this is one column. Beams are meeting here from that point to that point. Now, if the beams, consider the beams are meeting here. So, the loading pattern of the column will be like that. Okay, so from here portion, from this portion, the load is coming to this column. Now, so when the load A, this is the loading pattern, this is the loading pattern. So the requirement of this effective flexural stiffness is required when we have to determine how much load is coming to this column from the adjacent members. So when we are calculating the effective flexural stiffness, we have to consider for the adjacent beams and columns for that also. Now, what is the value of Kc? Kc equals to, it is written there, the Kc equals to Kc, the value of the Kc, that is equals to C into Kc equals to C into I by L, and Kb is equal to lambda into I by L. Okay, Kc is equal to C into I by L and Kb is equal to lambda into I by L. Okay, C into I by L and Kb is equal to lambda into I by L. Now, why it is now in case of beam, that is a Kb, the beam factor, we will always use lambda. Now, there is a small part written here. You can see in your note that if the beams are braced, then the value of lambda will be equals to 1. So if this is specified, that is the beams in the columns, this is the beams, these beams are the columns are based, that means they are fixed, then the value of the lambda will be equals to 1. Now, for the column, now comes the Kc factor. For the columns fixed at the base, summation of Kb, that is this value will be alpha, and beta 2, okay, beta 2 will be 0. Okay, and for column hinged at base, summation of Kb equals to 0 and beta 2 equals to 1. If Kb is equal to 0, beta 2 equals to 1, and summation of Kb is equal to infinity. Okay, if summation of Kb will be equal to infinity and beta 2 will be equal to 0, and summation of Kb for column hinged at the base will be 1 and beta 2 will be equals to 1. So this is the I is the moment of inertia about an axis perpendicular to the plane of the frame. That means moment of inertia of an axis perpendicular to the plane of the frame. Very important portion. When we do the math, we will discuss it. Now, L is the length of the member and C is equal to the correction factor as per table 35. There is table 35, that is the correction factor. It here the correction factor depends upon the factor n dash. What is the n dash? N dash is equal to the P by PE, that is the factor of n dash, where P is the applied load, the load is applied, and P is the Euler's elastic buckling load. What is the Euler's load? When we were in the third semester, we have discussed about the columns, where then we have discussed about the Euler's load, that is the formula pi square EI by L square, where I is the moment of inertia of the member perpendicular to the plane of the frame. Here also always the perpendicular to the plane of the frame. Okay, always need to determine that is the perpendicular to the plane of the frame. Then come the second option, second important factor, that is the slenderness ratio. What is the slenderness ratio? Ratio of the effective length to the radius, effective length to the appropriate radius of gyration. Now, why it is appropriate radius of gyration? Because always minimum radius of gyration is selected to minimize the steel requirement. If the radius of gyration is very much high, the steel requirement will be also high, and thus the total requirement of the economical concern will also come into the field. So always, to minimize the steel requirement, R minimum has to be selected from. So there will be two from the all the value of the radius of gyration, the minimum value will be chosen. So this is the value of the R minimum, I minimum by A. Now maximum slenderness ratio as per the table 3 of IS 800. If you go to table 3, that is in the, if we go to table 3, this is the value of the maximum value of the effective slenderness ratio. Okay, so depending on the member carrying compressive load resulting from the dead loads and the imposed load, so 180. Okay, so 180, so always the value should be less than 180. Now the type of section that are generally selected for a column member, generally the type of section generally selected. So here some of the sections are given in general. Okay, in general these are the some of the sections that are given, but sometimes depending on the section they are chosen. Like this is a double angle section, this is a double channel section, it may be a I section also, it may be a I section also, which can act as a rolled I section also, which can act as a column. Okay, so always this is the type of section. Now sometimes these are the rolled section, sometimes the rolled section are not sufficient to take the huge amount of load, so built up section are provided. These are the type of built up section. Four angles connected together, 4 angles connected by a plate together, 2 channels are connected together. These are the built up section which are provided in the design. So when in the next theory classes, when we will be designing the built up section, these theories will also require what is the built up section. Now coming to the design strength, that is the most important part, how to determine the design strength of the column member. The design strength is generally determined by this formula, by clause 7.1.2. this is the design strength. PD equals to AE into FCD. It should be always greater than the applied load. PD is equal to AE into FCD. What is the value of AE? Effective sectional area as per defined 7.3.2. If we go to 7.3.2, we will see the value of effective area. Effective area except as modified in class 4, that is that. Now the effective area AE is dependent on the various classes of buckling. How many classes are there? There are 4 classes. If we go in the 3.7.2, that is the buckling classes here. If we go to the buckling classes at 3.7.2, these are the buckling classes. Class 1 is the plastic class, you know that. Class 2 compact, class 3 semi-compact, and class 4 is the slender class section. So when we are discussing the AE, apart from the first 3, the fourth, apart from the fourth one, that is the class 4 slender, for all the 3 section, the value of the AE is equal to the cross sectional area for the members fabricated with bolt, rivet or pin. That means we don't need to deduct the net sectional area, that is the area of the hole for the bolt or rivet or weld or pins. We have to consider the cross sectional area for that case. Now for class 4, that is the slender member, the formula is like that: A is equal to summation of BEF into T, where BEF is equal to lambda L into TE, where lambda L is equal to the limiting width to thickness ratio of semi-compact section. We will limit width to thickness ratio of the section, and T is equal to the thickness of the section, and epsilon is equal to that value. And for circular hollow section, the area effective is equal to that value. So in general, we will not be requiring that, because all the section are in India. I have already told you when we are discussing the beam section that in India the section is either semi-compact or compact or plastic, not more than that. Okay, so FCD. Now FCD, the calculation of FCD, you all know the calculation of FCD is very much important, and it can be done in a number of way. First way is to calculate the FCD by this formula: FCD is equal to that. Okay, now the value, where a xi now the value of the xi can be calculated either from this IS 800 table 8A to 8D with appropriate value of KL by R and Fy. If you see table 8A to 8D, this is table 8A, the value of stress reduction factor xi for KL by R ratio and Fy. These four charts are given. This is the first procedure. The second procedure is by following this formula, that is the xi formula. Xi formula is by following this formula and calculating the 1 by phi plus phi square minus delta square. This is the formula. By calculating this formula, we determine the xi. Okay, and alpha is equal to the imperfection factor given in table 7. This is the table 7. The imperfection factor is given. Buckling class, for every buckling class the imperfection factor changes. So putting the value, we get the value of the xi. And the third procedure, the FCD can be directly calculated. The FCD can be directly calculated from this chart. Okay, table number 9A to 9D. Table number 9A, the design compressive stress depending on the buckling classes and the KL by R and the yield stress ratio. The FCD can be calculated by these three procedure. Okay, by these three procedure FCD can be calculated. So this is all the design parameters that we have considered. This is all the design parameters that we have considered. Now we will do some maths and examples. Okay, now first math is the calculate the value of the least radius of gyration. How to calculate the least radius of gyration? The formula of the least radius of gyration is equal to root over of I by A. Now the section is like that, is a built up section. So built up section, because of the built up section, the center of gravity, that is the CG distance, will also change. So first we need to determine the CG distance, that is the y1, A1 y1, A1 into y1 plus A2 into y2 by A1 plus A2, then calculating the CG distance. Now to determine the R minimum, we need to determine IY and IZ of the whole section. Now considering the IY, considering the IZ, so if this is the CG distance, we need to apply the rule of the parallel axis theorem. You all have done it in the plastic analysis. So we have to apply for the parallel axis theorem and to determine the IZZ here. Similarly IYY. Now when calculating IYY, we need to determine, now IYY pass through the middle portion, so the IYY there will be no need to determine the IYY by parallel axis theorem. By normal formula we are determining the IYY, so we have to check which value of the I is much more lower. So this is the I value lower, so R minimum will be RIYY. So this is the value of the RZZ and RYY, I by A root over of. This is the first math. This is the very normal math. Now second math is the important math. Calculate the design compressive load each the member shown here. So here the important thing is, this thing we know, but here is another part. So the CG distance will change. So first we have to determine, so this is the ISMC 400. So for ISMC 400 all the properties are written here. So now for ISMC 400 IZ and IY we know for the I section, channel section. Now for the total section, that is the channel plus the flange plate provided, we need to determine the total moment of inertia, that is the IZ of the total and IY of the total. Now the area of the plate is equal. Now first we are determining the CG distance, then the area of the plate we are determining. Now if this is 300, and then this is the width of the flange, that is BF. So if this is width of the flange and this is BF, so that will be equals to, this is also BF. So 300 plus 2 into BF into 16 is the thickness is equal to 16. So we are getting 8000. So putting the value here and applying the parallel axis theorem for both the cases I and Y, we are determining the the moment of inertia in both axes. Now here Iz is less than Iy, so our minimum will be based on the Iz. So our minimum will be because the Iz by A, that is equals to 157.92. Effective slenderness ratio KL by R. Here effective length is given. We can support the if the member is of 5.5 meter effective length. So effective length is given. So 500 by 34.82. Now we have to determine the FCD. Now we know the value of KL by R, we know the value of Fy. So for buckling class, now buckling class we have to determine. Now as it is a channel section, for channel section from table 10, for any channel section, or for any channel section or built up member, this is the built up member, so for that it is the C section. Okay, for C section, so always it will be a C section if for a built up member. So buckling class or built up members at any axis is equal to C. So for KL by R mean we are determining the FC is equal to Atho, design strength is equal to 4214.65 Newton. This is the Now comes a math which is based on the frame structure. The frame structure is given here. This is the story structure. These are the beam members, and these are the column members. Now all the things are given. The beam, horizontal beams are ISLB 325, vertical beams are ISWB 600. All the IZ value of this are given, and the columns are ISHB 400. The I section columns are given, where IZ and IY are given. The spacing of the beam members in the horizontal direction. In the Y direction, the spacing are 15 meter, 6 knots, 2.5 meter, and in the Z direction, it is 3 knots, 6 meter. So 18 meter distance and 15 meter distance. This is the Z direction, this is the Y direction. The ground to story height is equal to 3.5 meter. The story height. Now the total load 30 kN per meter square. That is the floor load, and Fy 250 is given. Okay, now what we have to determine is the effective length of the column marked in the plan. Okay, in Z direction and Y direction. Okay, now first unsupported length in Z direction. First in the effective length, this is in the effective length it is given that the L is the unsupported length. Okay, unsupported length. So you have to determine the unsupported length of the member. Now if consider this picture, if this is the column, a beam is connecting at this direction and another beam is connected at this direction. This is the Y direction, this is the Z direction. So when considered in the Y direction, when the unsupported length will be from the, if it is like that, from here to here, so this length will be subtracted from Y direction, and in Z direction this length will be subtracted, because then it is and here it is the unsupported length that we have done here. 3500 total length minus 600, because in the Z direction, that is this is the Z direction. In the Z direction the beams are ISWB 600, so minus of 600, and in the Y direction the beams are ISLB 325, so minusing 320, subtracting 325, we are getting the two values of the unsupported length. Now the total load coming to this C1 column, I have already told why we are calculating the effective flexural stiffness of beam and column joining at that point. Now total contributory load on the column, the story design load. Now if this is the C column and this is the spacing, total spacing, that is the 6 meter spacing here 6 meter space. If it is a 6 meter spacing, if this is a 2.5 meter spacing, so half, this is the beam, so half of the beam load from here and half of the beam load from here will come to here. Similarly, in the from the y direction, half of the beam load from here and half of the beam load from here will come to that point. So total load coming to the column is 6 into 225. This is the 6 and this is the 2.5 into 30. This is the 450 kilonewton load is coming to the total C1 column from adjacent beams. Now, being a frame, now this frame is braced against, now the ground, it has been said that the frame is braced, that is a non-sway frame. So for the non-sway frame, the formula that we will select, now if you see the formula here, we can see that for beta, which value of the k we will take, that the for non-sway frames, this value of the k we will take. So we are taking the value of the k here. So we are taking the value of the k here, that is equals to that value. Now beta 1 equals to kc divided by summation of kc plus kb. Now what is the summation of kc? Effective flexural stiffness in the z direction. Now if we see the diagram here, we are seeing that from the z direction, there is two beams are connected. So when we are calculating the effective flexural stiffness, so we will be we will be determining the effective flexural stiffness for two beams, because two beams are joined at that position. So number of beams will be equals to 2 into c into I by L. Now columns are based on both. Now column, here it is also mentioned that the ground story columns are fixed at the base. So columns are fixed at the base. So if we now see in my note that the value of n dash, that is the thing we need to determine, the value of the n dash, the value of the n dash will be based on the P by PE load. Therefore in table 35, n dash we have to determine. Now coming to table 35, which will be in, this is table 35. Now for fixed end, we will consider the value of the fixed end, that is the thing. So in our math, we have considered the value of 2.0 into 1 minus, for that this value, because braced frame, number one, it is the braced frame, and for that number one, it is the braced frame, and for that we have calculated that value n dash equals to P by PE. What is the value of PE? We all know that is PE is equal to the value of P pi by pi square, E pi square EI by L square. Now pi square EI by L square, this is the value. So putting all the values, I will be Iz, because here the perpendicular to the direction. So the column is in that position, and its perpendicular is that, so z direction. So here the putting the value of the Iz, so 28,083.5. So putting all the values, we have calculated that. Now similarly, two beams are also connected at C1. So similarly, KB will be equals to gamma B into I by L. Similarly, 2 into 1 into here also will be that value I by L. Now gamma will be equals to, gamma B will always be equals to now the value of gamma B. Now then again go to the formulation. It has been said that, I have already said that if the beams are braced, the beams are also braced in position, so gamma will be equals to 1. So putting the value of the gamma, that is equals to 1 here, we are getting, putting the value of gamma is equal to 1 here, we are getting the beta 1 here, we are getting the value of KB. Now beta 1 we have calculated from putting the formulas here. This is the formula. Now for braced frame, that we have shown in our drawing, for braced frame, that is the column fixed, KB, summation of KB will be infinity and beta 2 will be equals to 0. Okay, beta 2 summation of KB will be infinity, beta 2 0, and beta 1 will be having a value. So beta 2 we are putting a 0 as braced frame, so the value of K is equal to 0.58. Effective length of KL is equal to 1682 meter. Okay, this is the effective length. Now I have determined the value in the Z direction. Try to solve the problem by yourself. This is the y direction. Try to solve the y direction, determine the y direction. This will be your assignment. Try to solve this part by yourself, y direction part. Now next lecture, the next topic will be based on the design steps for the compression member, how to determine the design steps for the compression member. First, consider the formula, that is the AE into FCD. The AE and FCD, two terms are there. Number one term is AE and number two terms is FCD. This, from these two terms, AE unknown, FCD also unknown, because, and if the two terms are unknown, we cannot proceed. So we have to assume some value of the FCD. There are two ways. In absence of any data, assume FCD equal to 0.4 FY to 0.6 FY. It is the first solution. We will assume the FCD is equal to 0.4 to 0.65. In between that, if the length is on the higher side, if the length is higher, assume a smaller value, and if the length is on the lower side, assume a higher value. Okay, this is the first procedure. In the second procedure, also we can assume a certain value of the slenderness ratio. In for column 3 to 5 meter, a slenderness ratio of 40 to 60 is assumed, normal. For longer column, higher value of 60 is assumed, and for high factored load also, smaller value of slenderness ratio is also assumed. Okay, so these are all assumptions. They are the general basic thumb rules which we apply. They are not specified in the code that we have to take, that we have to take. Okay, they are generally thumb rules that we take always. Okay, so depending on the thumb rules, we determine the formula. Okay, so this is the value, how to determine the FCD. We will assume the FCD in that case. Okay, now cross section, the step 2, the cross section area required will be equals to AG, that is the cross section required, PU by the assumed compressive strength. Clear? The assumed compressive strength, PU is the applied load. Then depending on this AG, a allowable section, a trial section will be selected which has an area higher than or equal to the actual area that has been assumed. Okay, so the step 3, a trial section is assumed. Step 4, the effective length of the member is determined. Effective length of the member is determined depending on the end conditions. Okay, from table 11. Table 11 gives us the idea about the effective length of the member. From table 11, okay, we have to determine the maximum effective length of the column, and the slenderness ratio is calculated. Slenderness ratio, KL by R ratio, is calculated, and it should be checked by table 3, that is the maximum slenderness ratio. We have shown you that how to determine the maximum slenderness ratio. What is the maximum slenderness ratio for column? That is the 180. It should be less than that. Okay, now from the estimated value of the slenderness ratio, FCD, the actual FCD is determined. So we have got the actual value of the KL by R, the section we have assumed, so we can determine the KL by R. Then we have assumed the FCD. Now finally the design strength of the member is computed, which should be always greater than the applied factored load. This is the formula that we have always considered, the design factored load that we have considered, the design factored load. So this is the formula, so it should be always greater than the applied load. So this is the design procedure for normal columns, which will be doing for this lecture. One math will be there. Design a stanchion of 3.5 meter long in a building subject to a factor load of 550 kilonewton. Both the end of stanchion are effectively restrained in direction and position. Use steel of grade 450. Now first, it is given all the thing. Now there are two unknowns, as I have already said. So let us provide a I section. Consider we are providing a I section. Okay. So H by BF